Good morning, everyone. Welcome to the last day of the Quantum Week of Fun. I hope it's been very fun. Today we have a full day of quantum computing, direct product, quantum chemistry. And the first talk will be on exploring possibilities of near-term quantum computers for the simulation of the Hubbard model by Panagiotis Barkoutsos. Over to you.
Thank you very much for the introduction, and thank you very much for inviting me to talk about our work for near-term quantum processors and variational quantum algorithms. I will, using this talk, I will try to explain how we construct variational forms and what's the use of the variational forms for the variational quantum eigensolver. And using the iconic Hubbard model, I will try to demonstrate ways to think out of the box for generating the Ansatzes. And at the same time, I would like also to present an error mitigation scheme related to the calculation of the Hubbard model. So moving on, in the start of the talk, I will give a brief introduction of why we need variational algorithms and how can they help the calculations in near-term quantum processors. I will give the general framework of the variational algorithms, and I will talk a bit about the relationship between Hubbard model and the variational quantum eigensolver. Finally, I will touch a very important aspect of the recent research, which is the error mitigation techniques, and give an outlook of the perspectives we have towards simulating strongly correlated systems in near-term quantum computers. So, first things first, we need to go back in time. This is Alan Turing. And Alan Turing was one of the first people in computer science that tried to define how can we think about a quantum computer, classical computer, and what can a computer do. In general, a computer has an initial state. On this state, we need to apply different operations in order to be able to evolve this state. This is a mechanism that we're able to extract information from this state and try to solve problem. This notion that I just described is a simplified Turing machine. Later on in time, Richard Feynman came and said that we should use the same model for quantum computers. But here we will have to use different rules in order to be able to define a computer and be able to extract the information that we need from the state that we are generating. Richard Feynman also mentioned another thing that is quite nice, and it's one of the things that everyone in the quantum computing community has heard already. Richard Feynman said that nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. This phrase is really interesting if one thinks that we are going to do a quantum mechanical simulation of a quantum mechanical system. This sounds like really a good match. So a quantum computer has really the potential to solve such problems. Of course, beyond the quantum mechanical problems, we envision that the quantum computer will be able to tackle also classical problems. And one of the many applications which will go beyond the quantum mechanical problems will be finance, machine learning, optimization problems, and many others. In this slide, I list some of the applications that quantum computers have and have been proposed already in literature. And on this talk, I will mainly focus on problems that are related to quantum chemistry and physics. Beyond this, just to mention some of the applications that may be of interest for everybody in the field of material design or quantum physics and chemistry. We have the matching of molecular structures, we have calculations on the protein folding, but we also have optimization problems like the 3-SAT, like the traveling salesman problem. Also, we have finance problems like portfolio optimization, supply chain management. This is a clear sign that people have started thinking about how to use quantum computers for multiple problems beyond the vision of Richard Feynman of simulating quantum mechanical systems also. So how do near-term quantum computers work and what are the perks of using them? The answer to this needs to come from the thought that near-term quantum computers use physical qubits that are still noisy. We don't have universal fault-tolerant, error-corrected quantum computers that we can use with logical qubits, but we need to exploit what physical qubits in noisy processors allow us to do. In order to do this, and in order to find applications that can be done in the current hardware, we are using schemes that rely on hybrid quantum classical algorithms. This means that the part that can be done efficiently in a classical processor is outsourced in a classical computer, whereas the part that can be done in the quantum processor is outsourced in a quantum computer. This synergetic scheme allows for many advantages for current hardware. The first and important thing is that by using hybrid quantum classical algorithms, we can have short-depth quantum circuits that can really comply to the coherence and the dephasing time that we have in our current devices. In the same time, such hybrid quantum classical schemes allow us to go beyond classical trial states. So we can start thinking of non-classical trial states, and this provides the potential of improving the classical estimates that we have for different problems. At the same time, using a hybrid quantum classical algorithm, we are able to store in the quantum computer the state and operate the ground state and operate on this with exponentially fewer resources than the ones required classically. How a hybrid quantum classical algorithm works? Let's think for the case of quantum chemistry, which is one of the applications that really have flourished in the field. The first thing you need to do is that you need to define molecular Hamiltonian. This comes from the physics. It can either be an electronic structure Hamiltonian or a model Hamiltonian from quantum physics. And then you need to somehow map this Hamiltonian to qubits. There are multiple transformations that I'm going to talk about soon. Then, when you have your Hamiltonian into a qubit operator that can be measured in a quantum device, you need to generate a variational quantum chemistry algorithm, like the variational quantum eigensolver. Finally, after applying the algorithm, you can measure the molecular properties and the ground state energy of the system. The way that the variational quantum eigensolver works is shown in this schematic. You need to be able to parameterize your state with a set of parameters theta and prepare this state in a quantum computer and measure the Hamiltonian terms. When you do this, you are able to reconstruct the energy of your system, and by changing the parameters theta and redoing this classical feedback loop, you are able to convert to a set of parameters that correspond to the ground state. If you want to see this in a more mathematical way, the variational quantum eigensolver is shown in this slide. You start from your fermionic Hamiltonian, you apply the mapping, and you have a qubit Hamiltonian that is the sum of the different tensors of Pauli matrices. Then you prepare a trial state in a quantum device from a set of parameters theta, and with a classical optimization loop, you are updating these parameters until you minimize the energy of the system. The guarantee for convergence is not clear because this is a method that relies on the classical optimization, but we know that that the problem is bounded from the ground state energy due to the variational principle, meaning that there is no set of parameters theta that can really violate the variational principle in the limit of an exact calculation. With this said, let's start step by step and see what the variational quantum eigensolver can do and what are the different steps that we can work on in order to be able to enhance and extend the variational quantum eigensolver. The first thing is the mapping of the fermionic Hamiltonian to a qubit Hamiltonian. Fermions have different statistics than the ones of the spins. We need to apply different transformations. In order to be able to define the electronic structure of Hamiltonian in chemistry, we need to be able to calculate the one and two body integrals of the system. The solution of this problem comes when we solve Hartree-Fock calculation, and then the calculation of one and two body integrals is direct from this calculation. Then you need to express the annihilation and creation operators that live in the fermionic space into the qubit operators in the spins. For this reason, you use the Jordan-Wigner transformation, which is the most trivial since the 1930s. It's the most known transformation for this reason. Or you can apply some recently proposed transformations like the Bravik-Itaev or more lately parity and superfast encodings. The number of Pauli strings that you are going to have in your qubit Hamiltonian always scales in the order of n to the 4. For this case, we're going to use the Hamiltonian for the definition of the iconic Fermi Hubbard model, which was used for the study of strongly correlated materials. Hubbard model describes interacting spin half fermions on a lattice where each side can be occupied with up to 2 particles of opposite spins. This means that in order to encode a Hubbard model, we need 2 qubits for every side, one corresponding to the side up and one corresponding to the side down. After defining this, you need to do again the same transformations as the one that you applied for the chemistry in order to express the operators in the qubit statistics. With this, we are able to decide what is going to be the fermionic Hamiltonian and the qubit Hamiltonian that we're going to use. The other aspect that we need to think about is the classical optimizer. I do not want to elaborate a lot about the classical optimizer in this talk, but in principle, what is important to mention is that for noisy intermediate scale quantum computers, classical optimizer is an important aspect. Depending on whether you have noise or not, you may need to choose optimizers that are more robust to noise. Namely, for example, you can use SPSA optimizer, or if you want to do a classical simulation of the problem, you can use a plethora of other optimizers that you can find already implemented. So with this said, the last part that we need to discuss and we need to identify is that how are we going to parameterize our trial state? What do we need in order to make the trial wave function? And how can we introduce these variational parameters in order for the variational quantum eigensolver to work? I would like to introduce a little bit the variational forms that have been designed within the last years. And then I will try to compare them with state-of-the-art variational forms. In general, you start from an initial state that can be either the 0 state or any other state, and you apply a unitary operation parameterized from the variational parameters theta. The way that this unitary is described, is actually created, can be either from classically inspired algorithms, meaning that you take part that you try to translate in the language of quantum computers classical algorithms like the unitary coupled cluster, or can be genuine quantum algorithms that are tailored and made for the available hardware and for the near-term quantum devices. What is important to know is that whenever you're going for a more specialized wave function, trial wave function, like the case of the coupled cluster and the different variants of the unitary coupled cluster, the problem specificity increases a lot, meaning that this can be used nicely for chemistry and fermionic problems. But at the same time, the complexity of implementation seems also to be increasing. Whereas going towards heuristic variational forms that are hardware efficient, the ease of implementation is much better, so you can really do it in the near term quantum hardware, but the problem specificity is much lower. I will try to show you a little bit, I will try to explain why the specificity changes and what's the main differences when we think about quantum chemistry in the slides that come after. So the more general case of the variational form in the heuristic efficient ansatz is the ones that I will show you now. We have the real amplitude variational form, which mainly consists of a layer of RY rotations parameterized from theta parameters and 2 qubit entangling gates, and followed by another block of single qubit rotations. The last 2 blocks are repeated d times in order to introduce enough variational parameters to converge your problem. What is the advantage of this variational form is that you can actually use all of the native gates that you have available in your hardware without really limiting yourself in a certain structure. For the layer of entangling gates, you can use any type of connectivity that's available in your hardware, with the limitation that you need to repeat it d times. At the same time, the 2-qubit entangling gates require is the gates that we have available in your hardware, whether it's C0 or Control-Z gates. The another version of the same variational form that we call efficient SU2 variational form allows also for the introduction of a layer of RZ rotations. In this way, you can search the whole space in a more efficient way comparing to the real amplitudes before. Here we have the 2-qubit entangling gates again, and a layer of an RY and a layer of RZ rotation repeated d times again in the same fashion. Another way that you can parameterize your tile wave function with hardware native gates is the excitation preserving circuit. In the excitation preserving circuit, you need to ensure that you start your calculation with the right number of particles and then allow for different parameterized entangling gates. So you will have two qubit gates that are parameterized and always allow you to stay in the right space of particles, meaning that you have to explore a much limited space and not the whole exponentially growing Fock space of the system. Again, here you can introduce layers of RZ rotations with different variational parameters. It's important also here that whenever you have the 2-qubit parameterized gate, you need to be sure that you are using the natural connectivity of your hardware and you connect the qubits one with the other. In general, a 2-qubit parameterized entangling gate can be decomposed into C-nodes and rotations in the form that I show you here. It's important to mention that, I'm sorry. Is it charging for me? Can you hear me? No, it's not charging.
We can still hear you and see you fine.
Sorry.
No worries.
No, it's okay. Sorry. Okay, going back to this, yeah. It's important to know that using this variational form, you can conserve the right number of particles, as I mentioned, without the need of searching the whole Fock space. Another way that you can do it is that you can start using classical quantum chemistry approaches like the unitary coupled cluster singles and doubles. The reason of choosing the unitary coupled cluster instead of the different versions of the coupled cluster is exactly because in the quantum computer, we know how to implement unitary operations. The way that the unitary coupled cluster looks is the one that you see here. You start from the electronic Hamiltonian and you parameterize your wave function with the cluster, with exponentiation of the cluster operator. The cluster operator T is parameterized with cluster amplitudes theta and composes from the single excitations and double excitations. With this form, you can express it and you can apply it in the Hartree-Fock state, which is the very good approximation for the solution of the problem. So it's a good initial state. And then you need to trotterize in order to be able to map it directly to a circuit. Then applying the Jordan-Wigner transformation in this, you end up with circuits that have the form that you see here. It's clear that for the single qubits, you have these ladder operations of C-nodes, where the dust C-nodes are consecutive C-nodes between the neighboring qubits, for the excitation of the occupied orbital P to a virtual orbital R. This circuit needs to be repeated 2 times for every single excitation. Whereas for the case of the double excitations, you need to repeat the circuit that you see here 8 times for each double excitation. Looks like this is not the way to go due to the really increasing circuit depth that is required here. So the circuit depth is the limiting factor of the applicability of the unitary coupled cluster singles and doubles. Again, using it allows you to stay in the right particle space that you need to define in your initial state for the calculation. So a summary of the variational forms that are already proposed in the literature is shown here. For the case of the real amplitudes, the number of parameters scales with the number of qubits n and the depth of the circuit d linearly, and the same holds for the case of a linear connectivity for the entangling gates. The advantage of using the real amplitudes and the efficient SU2 is that in principle you have short depth and you have a hardware efficient circuit. But for both of them, the particle and the spin conservation cannot be done with this variational form. When you are using excitation preserving with linear connectivity, so with parameterized 2-qubit gates, the number of parameters scales as n plus d times 2n minus 1. And for the fault connectivity, you need to do the combination of these two gates on the n qubits. Here we have again a moderate circuit depth comparing to the unitary coupled cluster singles doubles, but we can guarantee the particle conservation, provided that we start from the right initial state. For the unitary coupled cluster, the number of parameters is the same as the number of excitations considered for your system, and the number of entangling gates is a prefactor of the number of excitations, depending on how many orbitals you are considering. In general, for the unitary coupled cluster, we have very large circuits, but we have the particle and the spin conservation in the system. What is important to know is that out of these variational forms, there is no guarantee that the chosen heuristic ansatz or even the UCCSD ansatz will always converge to the ground state of the system due to the optimization limitations. The ground state may not be described by the family of variational ansatz that we described before, and may require significant increase in the number of D for the heuristic, in the number of repetitions of the blocks in the heuristic ansatz. For this solution, the solution that we can propose is that you can try to constrain the Hamiltonian to keep it in the right sector, or try to increase the depth of the ansatz, as I said, increase the D. In general, finding the ground state of a k-local Hamiltonian is a QMA complete problem, as demonstrated in the literature. There are certain cases where the unitary coupled cluster, or actually the coupled cluster classical ansatz, fails to describe the problem, whereas the quantum equivalent one allows for a better description and a more exact solution to the problem. This is something that we recently noticed in our paper, where we actually used the Hubbard model, so the model that I'm going to use to benchmark the variational forms today. And we showed that the classical method fails to describe a 6-side periodic Hubbard model, as you can see in the blue crosses here. Whereas, when we're using the unitary coupled cluster singles and doubles, which is the red line, and the different variations of the unitary coupled cluster where we truncate the number of excitations, we're able to describe much better the ground state along the U over T profile. You see that the truncation introduces some errors in the system, but we are able to really see that we have quite good replication of the ground state result for the unitary coupled cluster comparing to the classical method. Now, this is a clear indication that we should start thinking of more variational forms and more ways to describe the Hubbard model using a quantum computer. For this reason, we said that we would like to think and try to tailor a new variational form for the Hubbard model. Again, we went through the same path and we started thinking about arbitrarity, specificity of the different Ansatzes, and we came up with a solution of the quantum optimal control inspired Ansatzes. This is a work that was done in collaboration with University of Sherbrooke, and we started by thinking of the heuristic ansatz, or the hardware efficient ansatz, as an arbitrary ansatz, and the variational Hamiltonian ansatz, where we actually encode the Hamiltonian of the system, as a problem-inspired ansatz. We also used the different version of the variational Hamiltonian ansatz, where you introduce the fermionic Fourier transform. The ansatz that we came up with, which we call QOCA, or Quantum Optimal Control Inspired Ansatz, has two specific versions, the short and the longer one, which is problem specific and is inspired from the classical optimal control theory. So the horizontal lines here represent the qubits, and these are the blocks that correspond to the different parts of the Hamiltonian in the repulsion and the hopping operators in the Hubbard model, in this case. What is the advantage of the quantum optimal control inspired ansatz? And this is exactly that what I mentioned before. We really need to be able to confine ourselves to the right part of the space in order to solve the problem. And this is something that the variational Hamiltonian ansatz does quite well. But for the case of the quantum optimal control inspired ansatz, you are able to go a little bit out of the space of the solution. So you can just try to navigate yourself towards the solution in a faster way without the need of being confined in the right particle space. And this is exactly what we want to have as a variational form. Now let's try and see in a mathematical way how the QOCA works and what the QOCA is. The QOCA in principle allows you to have a problem Hamiltonian, which is specified as the Hamiltonian, and you need to introduce some driver Hamiltonians. The parameterized wave function on the theta and delta parameters is shown here as the product of the exponentiation of your Hamiltonian and of the drive Hamiltonian. So here we have a trolley step between the two. The drive Hamiltonians that we are using are not time dependent for this case in order to reduce the number of variational parameters, and are the ones shown here. We apply the Jordan-Wigner transformation on the drive Hamiltonians, and we end up with strings that have this form. The equivalent form in terms of qubit operations is shown in the panel B, where you have the Z up to X Z to X tensor string, and this is encoded in the formalism that we have here. So this is the general circuit that is used for the QOCA, and this is the definition of the different gates that we are using. Again, note that we have the same notation as in the case of the unitary coupled cluster, where the dashed line control NOT gates correspond to a ladder of CNOT gates starting from the top qubit and going to the very bottom. In general, the way that the drive Hamiltonian, so the second part of this equation here, is written in the form that we have here. And this is exactly the way that we construct the circuit that we show you in the A panel of the figure. It seems that this circuit is also quite hungry in terms of circuit depth and requires a significant number of gate operations to be implemented. So this does not, again, look so friendly for near-term quantum computers, but we still thought in the long run and tried to understand how this ansatz can be used and what can be the perks of using this ansatz for near-term quantum computers or even longer-term quantum computers. For this ansatz, we noticed that we have the case where we actually have a strong dependency on the initial state for the variational Hamiltonian ansatz. For the case of the solid line, we start from the plus state. Oh, I forgot to mention that for all the simulations, we decided to use the half filling of the Hubbard model, which is which is the most difficult case for the Hubbard model. And for the solid line here, you see that for the case that you start with a plus state, the convergence with the variational Hamiltonian ansatz is very difficult. For the case that you start from a ground state of the hopping operator, again, the convergence does not happen with good fidelity. Whereas for the case that you start from a superposition of the hopping operator ground states, from the T operator ground states, you are able to converge with a reasonable number of repetitions in your blocks, or reasonable layers D. Whereas for the case of QOCA, independently of how many, of what is your initial state, you are able to converge to the solution of the problem with quite good results. This is really nice to see because it seems that the QOCA is quite robust to the initial state, to the choice of initial state for your simulation of the system. In the terms of the Fermi Hubbard model, we try to use the QOCA scalable, where we actually repeat some parameters, we reduce the number of variational parameters needed, and the short QOCA version, where we don't use the hopping operator. And for this case, we are able to converge to the solution for most of the cases with fidelity in the order of 3 or 4 nines, depending on the size of the system. The upper panel is for a Hubbard model, Fermi Hubbard model with 2 by 2 lattice, and the one below is 2 by 3. So 8 and 12 qubits, respectively. The QOCA, without any approximation, so not scalable or not short QOCA, always converges with quite good accuracy, whereas the variational Hamiltonian Ansatz seems to have problem converging in most cases, and the heuristic efficient Ansatz seems to correct, but still does not go in such high fidelities comparing to the QOCA Ansatz. If you would like to see in more in numbers, in the table that we have here, the QOCA seems to outperform any other ansatz that we have used, including the variational Hamiltonian Ansatz, the heuristic efficient Ansatz, and the Fourier transform Hamiltonian Ansatz. The same holds for the case that we have 12 qubits, but here clearly seems that the problem is much more difficult to be tackled. The important thing is that the number of parameters that we have per layer, you see that we have quite many parameters, and the number of synods is also quite high for the case of the QOCA. Another aspect that we noticed in the quantum optimal control ansatz is something that I mentioned before. You see here that for this case, I mentioned that we need to go out of the right number particle space in order to be able to converge to the ground state solution. And if one monitors in the whole VQE process, the number of particles, this is normalized to the right number of particles, you will notice that the QOCA has quite, that seems that to not really converging towards the right ground state until the moment that you are the most far from the right number of particles throughout the whole optimization process. And this is something that clearly shows us that we are not following the path like the one in the blue here, but we are going through the path that is in the dark red. And this is quite nice because we are able to converge by using a path that hopefully is shortest. We still need to think how to make the QOCA more applicable for near-term quantum devices. And we need to find ways to shorten it and be able to reuse the information properly and more efficiently. The question after this is that, okay, can we actually do something that has applicability in near-term quantum devices and can be used? And what do we need in order to be able to do it? The question is, in principle, the answer to the question is that we need to use error mitigation techniques. We need to start thinking of how we can use the physical qubits in a more efficient way and get better results out of what we have today. In the literature, the two techniques that are proposed and we used for the results that I show you in the next slides is the Richardson extrapolation, which is an extrapolation technique that allows you to extrapolate back to the zero noise regime by introducing a stress factor. The method was introduced in the Nature paper of Cantala for the case of the chemistry and quantum physics models. And the readout error mitigation, which is actually a technique that allows you by post-processing to correct the probability to measure the wrong state. The problem is the problem of the first technique, although it's a great piece of work for sure, is that it requires you to have low-level access to the hardware in order to be able to stretch pulses and use stretch factors to introduce extra noise. Whereas for the second case, the number of states that you need to prepare are too many, scales actually exponentially. And in order to make this calibration matrix is something that would require quite some calculations in the quantum device. For this reason, we did think of a new way of mitigating the errors based on a hardware agnostic error mitigation algorithm that can be used in the near-term quantum computers and is mainly inspired from the classical Lanczos method. The technique that we propose allows for mitigation of the different sources of noise that you may have in your hardware, with the sole cost of an increase in the number of measurements that you can do that you need to do in order to reconstruct the expectation value. In this work, we numerically demonstrated that we can have errors of quite low errors, very close to chemical accuracy for chemical systems, and that this method allows for the error mitigation. The way that this works is that you need to construct the density of the Lanczos according to the expression that we have here, and reconstruct your expectation value based on this density. The number of measurements that you require always scale as n squared times n, where n is the number of terms that you need to measure for the operator, for the observable that you want to measure, and n squared is the number of terms in your Hamiltonian. We applied this technique for the case of the hydrogen 2 molecule using 4 qubits, so in the Jordan-Wigner formalism without any reduction in the number of qubits. And when you do not use any kind of error mitigation technique, the probability distribution function is the one shown here. Sorry, I forgot to mention that the results that I show here are in the equilibrium point for the hydrogen 2 molecule with 4 qubits. We used 8,000 shots for every experiment, and we repeated it 100 times. When you are using the Lanczos algorithm that I mentioned before, the probability distribution function is the one shown in blue. You see that it's much closer to the non-noisy result, which is the dust line, and the exact result, which is the white solid line. The same goes if you use weighted least squares out of the 100 repetitions of the experiment, or you use an arbitrary parameter d in order to reconstruct the energy from the different experiments, or you use the cube. You see that for every case, we are able to get results that are much better comparing to the ones of the non-error mitigation technique. So no Lanczos application. We also combined this with the extrapolation to zero noise by introducing more and more control to qubit gates, so more control phase gates. And you see that the errors are quite high, the error bars, but back in the extrapolation to zero noise, we are able to converge to the solution of the non-noisy result quite well. Whereas for the case that we do not use the error mitigation technique of Lanczos, we do not have so good results for the 4 qubit system. Clearly seems that we have a more stable solution and more close to the exact solution by using this technique. This is for the case of the hydrogen molecule through the whole dissociation profile. You see that the errors are quite low in the order of millihartry, and this is a quite good result. We really compare this with the state-of-the-art results, and we see that we are not far from state-of-the-art. For the case of the 4 qubits, we still have more errors, but still we get much better result comparing to the bare VQE calculation without any error mitigation. We did the same calculation also for the case of H3, where we vary the position of the top of the triangle by stretching it, and also for the Heisenberg model by changing the J factor on the Heisenberg Hamiltonian on the orange, on the pair of sides on the orange here. For both cases, we are able to reconstruct the profile of the energy along the profile quite well, And we clearly have much better result if we compare the green results of the bare VQE with the orange results that come from the one of the Lanczos mitigation scheme. So later today, my colleague Igor Sokolov is going to talk about molecular dynamics and how we used the Lanczos error mitigation in order to do calculations like the one I show you here. So his talk is going to be today in 4.5 hours, so depending on your time zone. And we use this technique also for the case of the Hubbard model in order to be able to simulate and find the results of the phase transition from a fragile mode insulator to a band insulator for the Hubbard model. The results are quite good, and we are actually able to capture the transition between the different phases. For this reason, we were able, for this problem, we used an adaptive RY-RZ variational form, where we actually started by changing the number of RY and RZ gates, so the efficient SU2 that I mentioned before. We just changed the number of gates that we are introducing, and we were varying the ansatz until we have quite good convergence. You see that the convergence is quite good, and with the error mitigation scheme that we introduced, we were able to capture the phase transition quite nicely. So this work is in preparation, and we will have a paper in the archive soon. But as a final summary of my talk, I would like to say that the variational forms are a key component for the application of variational quantum eigensolver in near-term quantum processors. And the solution that we're going to acquire is highly dependent on what variational form we are using. Designing a new variational form has the potential to outperform generic variational forms that I described before, but this may lead to solutions with really high circuit depth or very complicated structures. Finally, noisy-term quantum processors require error mitigation techniques to acquire meaningful results. And this is something that needs to be pursued further, and there is quite some literature around it. I would like to acknowledge my colleagues Philip, Igor, Ivano, Alexander, Augustine, Alexandre, Mark, and Titus contributed a lot in the papers that I showed you in this talk. And I would also like to say that thanks to the whole IBM Quantum team and collaborators in Zurich and worldwide. So thank you very much, and I'm very happy to take any questions.
Thank you very much for the nice talk. You have a huge amount of results there. It's very interesting. It has stimulated a lot of questions on the Slack.
Mm-hmm.
So I will just read them out. So the first one from Adriana Meijer van der Grind. What is the reason that your swap RZ has 4 CNOTs since there is a minimal form for any arbitrary 2-qubit gate using only 3 CNOTs?
Mm-hmm. So in principle, what I showed you is the way that you can decompose the swap RZ in the most straightforward way. There is a way that you compile it with using only 3 CNOTs, definitely. But in principle, there is hardware architecture that have the swap RZ, the 2 entangling gates of the swap RZ directly implemented on the hardware. So this is just an easy compilation that I did. You can find also different ways to decompose.
Okay, so the next one from David Munoz Ramo. In the example you showed for the QOCA, if that's correct.
Yes.
It seems that the number of parameters to optimize is similar to the one what finds in the hardware efficient case. Do you think there may be problems with the optimization once you move to larger systems?
Yeah, so the optimizer is always an interesting point that one needs to consider in a variational algorithm. So there is possibility that we have problems with the optimizer, but for most of the cases, because we use the problems that we still have access to the exact ground state, we try to be sure that we're actually converging towards the right ground state. But the optimizer can always be something that needs to be chosen very carefully.
Do you have a preference for real systems?
I mean,
hardware.
in terms of noisy simulations, I'm always trying to use SPSA since the one that is claimed to be robust to noise. But for the case of classical calculations, we used Cobila, we have used SLSQP, BFGS, so there are many choices.
Yeah.
There is also recent literature about introduction of Bobiqua or IMFL, so there are many optimizers that one can try.
A whole zoo of optimizers. On that note, you noticed in your symmetry breaking optimization that when you were far enough, the most furthest away from the particle number states, it sort of kicked the optimization. Do you have any physical intuition of why that is the case?
So this is mainly numerical and not so much a physical intuition. So it's not clear why this is happening. So there can be many interpretations, but I guess there's none of them is physical.
Yeah. Okay. So, yeah. I mean, potential early surfaces are incredibly difficult to understand. Can you say a few more words about the adaptive RY-RZ ansatz? This is from David Munoz-Romo again.
Yes, sure. So first of all, this is a work that we're going to publish very soon, and you will see that this is an ansatz that works quite well for the case that we investigated. And in principle, what we are doing is that we're having a series of gates, and by varying, so by activating and deactivating some of these gates, we're able to construct and reconstruct the different ansatz every time. So we are just enhancing and increasing the layer by one gate, for example, and then we see if this has an effect. What you can also do is that you can also do a metropolis type of algorithm where you actually use the gates and start using a random combination of different gates in order to reduce your ansatz, and then see if this is going to help towards the convergence and the solution of the problem. So the details will come soon.
Okay, so the next one is from Bruno Sinjin. In the Lanczos algorithm mitigation scheme, the scaling in the additional number of measurements seems extremely large. In chemistry, the number of terms in the Hamiltonian scale is quadratically with respect to the number of qubits or orbitals, and the number of terms for the observable also in general be quadratic. This makes the number of measurements of the mitigation scheme scale n to the 10 with n as the number of orbitals, making this method extremely expensive. Is this method doable apart from very small systems? Direct question.
So this question is very hard to be answered. I mean, we also have done quite some thought, but we came up with the idea that actually we did not come up with the idea, but we thought that when you group the Pauli terms in the measurement basis, as it was done in the paper from Sergei Bravi in the grouping of Pauli terms, you can really see that you can reuse many terms from the previous Hamiltonian. So we do not have a different scaling factor that I can tell you that the scaling factor is a certain number. But we know that when you're using these grouping techniques, you have much better scaling compared to the nominal scaling of the algorithm. So you can always group and reuse measurements and reuse different Pauli terms to reconstruct the different terms. So we hope that this can solve a little bit the scaling issue.
Okay, so the next one from Marco Di Janeiro. Is there a set of thumb rules to translate a given molecule to a fermionic and spin Hamiltonian? How does the size of the Hamiltonian scale with the number of atoms or orbitals?
So can you repeat the first part? I'm sorry.
So is there a rule to translate a given molecule to a fermionic and spin Hamiltonian?
Is there a rule to translate? Okay, I don't fully
I think it's been partially answered in the Slack. Okay, so
let me say some general words about how we map a molecule in a quantum computer, and hopefully this can cover the answer to this. So maybe I can go back to the slide. Just give me 1 second. Oops. So how we map a molecule into a spin Hamiltonian. So we need to start with the second quantization Hamiltonian. It's the one that you see here. So the electronic structure Hamiltonian. What you need is that you need to find a way that you encode your annihilation and creation operators and how you get the one and two body integrals of this Hamiltonian. The one and two body integrals is the process that I described in the presentation where you actually solve the Hartree-Fock calculation and then you calculate the integrals for the one and two body. The way that you map your annihilation and creation operators in the spin statistics of qubits, you're using classical transformations like the Jordan-Wigner or the Bravik-Itev, the parity, and the superfast decoding. In the direct mapping, each orbital corresponds to one qubit. This means that the scaling and actually the rule is that when you're going to do this transformation, each annihilation, each creation operator is going to express in the Jordan-Wigner formula with these equations that we have here. And each orbital is going to be represented by one qubit. So this is more or less the answer.
Yeah, that was perfect. Thank you. I have a question from Paglan Lower. Can you talk a little bit about the error mitigation techniques? How do you rank them in terms of reducing error?
So the error mitigation technique, the first one that I mentioned, it was the Richardson extrapolation or the zero noise extrapolation, where you actually increase the errors that happen in your system by a stretch factor. So whenever you are operating a pulse in a certain time, you just stress it, and then this induces more noise. Then having different levels of this noise, you are able to extrapolate back to the case that you would have zero noise, which corresponds to the exact solution. Now, about the case of the Lanczos algorithm, what you need is that you need to do multiple measurements in the different, let's say, powers of the Hamiltonian. And when you're going back, you have the density of the Lanczos that you apply in your observable before measuring. And in this way, this allows you to mitigate for the error. It's the same way that a classical Lanczos algorithm works in the Krylov subspaces.
I think there are a few more questions. Let me just look. So have you tried using like these new fermionic swap gates at all in your work?
Yeah, the fermionic swap gates is very close to the swap RZ fermionic ansatz. So we have actually we have used it, we have tested. It's quite interesting ansatz that was proposed by the team in Harvard and Google. And it's also, it's a quite interesting ansatz. Yes, we have used it.
Okay. And I guess one final question from myself. Well, we still have 5 more minutes, but so when you're talking about the phase transition in the Mott insulator for the Hubbard model, are you doing that with the dynamical type approach? How are you analyzing the phase transition?
So in principle, we scan the whole profile. Here. So you see that we have the okay, this is a special system that I don't want to go into details right now, but we have the second nearest neighbor hopping terms, and we are going through the T over T in order to find this transition. So I'm happy to discuss it in a week or so when we will have the archived paper in more details. So I just wanted with this slide, I just wanted to show that we can use really the proposed ansatz and the proposed error mitigation technique to actually capture physics problems that are of interest.
All right. I'll ask one more question then, as we have 5 more minutes. The ansatz that you say is a mixture of the time evolution and the heuristic one. That would seem like a very nice idea, but I was a bit confused. Could you speak a bit more about that?
Yes, sure, but I didn't get which ansatz you're referring to.
It was in the beginning slides. Well, not the beginning. You introduced a series of time evolution methods and ansatzes. and it was the ansatz that you use for. Yeah, sorry.
Mm-hmm.
So go down, probably about slide 25, I think.
Is here? No.
No, maybe before.
Okay.
Sorry.
This is the unitary couple cluster.
I think it had like, it was a ZX, had lots of ZX gates.
Okay, this was the QOCA.
Yes, of course. Sorry.
The drive Hamiltonian, yes. Here.
Yeah.
Mm-hmm. So sorry, go ahead.
Oh, no, you explain. Sorry.
Okay, so the way that the quantum optimal control inspired ansatz works, that we have the problem Hamiltonian, and then we are introducing a drive Hamiltonian, like the one that you see here. This is the way that the optimal control work. For example, algorithms like Grabber, also Grape, sorry. The unitary matrix that corresponds to this ansatz is split it in a way that you have your problem Hamiltonian, and then you have your drive Hamiltonian coded in the system. The drive Hamiltonian has the form that we have here, because for simplistic, we omit the time-dependent part, and we fix it in 1 and I. And we have the H1 and H2 terms, which we need to map with the Jordan-Wigner formalism. And these terms are the ones that are depicted here. So this is the drive Hamiltonian. So this part of the ansatz is encoded in the fashion that you have here.
Okay.
And if you would like to see it in a more big picture, you have to encode your Hamiltonian, problem Hamiltonian, so the repulsion, the hopping operator, and then the drive terms.
So would you say this is a time evolution type method?
Mm-hmm.
Yeah. Okay, cool.
It's like the variational Hamiltonian ansatz.
Okay. Excellent. Okay, so thank you for answering all the questions.
Thank you very much. It was great.
And I invite you to the Slack to answer some more questions in more detail.